influence how much money or income you make. Okay, that's simple linear regression. So what we're going to estimate in a linear regression in this context, for example, is to find the beta, the coefficient of that education. In other words, to determine by how much income will change when your education level changes. That is the betas, the coefficients. That's measuring the giving information in relation to one, the direction of association, then the degree, the extent to which the effect can be realized. All right. One method of doing this is through the ordinary least square estimations. There are various kinds of regression estimations. We have ordinary least square, we have two-stage least square. There are different kinds of regression estimations. But for now, we are dealing with the ordinary least square estimations. The ordinary least squares seeks to find the line of best fit. Okay, the line, I think I've dealt with it. That's what in your second year when you're dealing with quantitative methods, quanti, where you try to identify a line that was passing through an array or a cloud of points. But the line must at least be close to most of the points as much as possible. That's the line of best fit. That's the ordinary least square approach, where we are looking for the line of best fit that describes how the variables relate. So, okay. And the essence is to try and, or the line is to try and minimize the errors. The errors are distances from the line. So the next graph will show you. So the line you can see, you are seeing on the screen now is an example of a line of best fit, a linear regression line. Is that okay? And the points, okay, just by the lines where you are seeing some arrows to the line, okay, those are the actual points, okay, of the data. And the essence of this line that we are going to minimize. In other words, you find a line where the distances between the main point and the line are smallest or very small. That is the minimizing the errors, the sum of squared errors. That is the intention of the linear least square regression estimations. So we want a line that minimizes the sum of squared errors of that line of best fit. Okay. In other words, we want to predict some quantity based on some equation, but that equation must be such that when we are predicting, our margin of error is as small as possible. That is in simple terms. Is that okay? Is it okay? Hello?
Yes.
It's okay, right? All right.
Yes, please.
So we want to look at another example using the capital asset pricing model. Okay. We know CAPM, trying to estimate the returns of a particular asset in relation to the market premium, okay, or the market returns. Is that okay? So as proposed by Ross et al., the excess return is equal to the risk-free, which we are seeing here as the alpha in this equation. So in this equation, RI minus RF measures the excess return. Is that okay? In other words, your return on the asset from the risk-free, the SS, which I explained at the time to you. And then the RF minus RF is measuring the market premium, the return of the market above the risk-free rate. The beta in this equation is measuring the risk of that asset you are interested in. In other words, in this case, you're going to use the GCB Bank shares as an example. We want to see the risk of holding a GCB asset. Okay, the risk of the returns of holding a GCB asset. So we want to use this model to try and estimate the risk of holding the GCB asset or stocks on the Ghana Stock Exchange. Okay, and then in this context, our risk-free rate, we are using the Treasury bill. So now, the example here I took from your book directly. Is that okay? I think it should be on in the second unit. I think somewhere around unit section 3 or so. If you want to refer to it. If you are there, you can make reference. You can just give your colleagues the reference page if you are there. Especially if you are with the manual book. So I'm not going to go back to the software to estimate. So you're going to use the output from the book and interpret from there. Okay.
So, and so sometimes even the soft copy, the diagrams and other things, we don't have them. I
The
don't know
what?
why. The
The
diagrams,
diagrams.
some of the diagrams. Me, I don't have it in my soft copy. I don't know why.
Oh, okay. Then perhaps you can
And
have
the book too, we don't have it.
all right. Okay.
That's why I said
So
we like your slides.
okay.
Yes.
So
If not,
it is well. So my slides I keep updating. So when I finish, I'll send you this one too, which is additions and modifications to it. Is that okay? So I don't want to be building different slides. So I keep on adding up. Okay, so I'm around page 45 of unit 2 section 3. That's where the for the example is. Okay, I don't want to bring everything in here, so I'm just referring you to the page. Okay, so in that context, the data was they took the weekly returns of GCB stocks on the market. Is that okay? Another one you can use the software to estimate the returns. We have done returns already, simple return, log returns, whichever one you want to use, you are free to use. Okay. And then we had the market return measured by the all share index, okay, which currently we refer to as a composite index. I showed you that time, okay, on the Ghana Stock Exchange. And so we want to use this three key variables: treasury bill rate weekly, um, GCB return weekly, and then the market return by way of the ASI, all share index. Now, the GSC no longer uses ASI. Now they are using the composite index. Is that okay? And then you see that another one to the which you saw on the screen at that time, which is the financial stock index FSI. So they have two indices there now: GSC CI and GSC FSI. All right. So in this example, we're using the GSC CI at least, or the ASI, which you see in your book, which is the all share index. Is that okay? And so you determine the return on the GCB Bank by essentially deducting the GCB return, the TB rate from the GCB return. That'll give you the excess return. So that gives you the variable on the left hand side. Is that okay? Of the equation. For the market return, essentially is the ASI minus the risk free. Is that okay? That will give you the market premium. Is that okay? Okay. And then the beta, the alpha is the risk-free rate. So once these three variables are known, put them into your eViews regression, the regression eViews software, and then you go to quick estimate, and then you can follow the steps in the book, and then you estimate the equations. So let's see the output, and then we can interpret from there. So the output will now give us the betas. So I'm doing in regressions, the beta of the GCB bank stock. Is that okay? Then we'll now interpret to see what it means and so on and so forth. All right. So that's the idea of this example. Paraphrase. So this is the output from the estimation of the eViews software. You can see that the table has different columns and different rows. Okay, but essentially this output is seen from three different segments. Is that okay? The first part ending at observations 516, okay, upwards is the first section. Then from the variables C up to the MP, another section. Then from the R squared downwards to the last probability values F statistics is also another segment. Is that okay? The first one is mostly giving you quantitative information about the estimations. So you can see your dependent variable is ERGCB. You're using the least square method. You have a sample period of 6th August 2023 to 8th June 2003 to 21st April 2018, about 10-year or so period. Then we have 516 adjustment observations. In other words, if you multiply the time period and items involved, the days in the weeks involved, you have 516 observations or data points. That's information for the estimation. The actual things I'm going to use is the C and the MP, the second segment, plus the last segment. That's where we are going to interpret from. Is that okay? So let's see what this means. So our C here is our alpha, our constant term. Is that okay? Then the MP is the market premium. So the coefficient of the MP is our beta in this context. Is that okay? We will discuss very soon the various segment and what it means. Diagnosis will come there. But let's see in this context, what is our beta? So our beta in this context is a 0.330716. Is that okay? But is that figure significant or insignificant? In other words, should we hold it as a good variable that can give us an explanation of the change we see in the excess return of DCB or not? That is seen in the three other things beside the coefficient: the standard error, the t statistics, and the p-value. Is that okay? Hello? We will deal with these three things very soon. For now, we are only trying to interpret the beta from this estimation. Is that okay? And so, since the p-value of the beta or the MP in this context of which is 0.33 is significant, you are looking at the p-value. You see the prop there. You have 0.000. I see that connotes that that variable is significant. It means that we can rely and use the estimated beta of the MP. Hello? So if we are from the estimations, we can write the final equation as ERGCB. In other words, the excess return of DCB is equal to 0.330716. Well, I didn't bring the alpha, which was already in the initial equation here, because the alpha, which is a constant in this equation, was insignificant. Look at the p-value of the C is 0.7082. It's above 0.05, which I've learned in your statistics earlier. Is that okay? And so when the p-value is above the level of significance, then we reject the null. So we fail to reject the null. So in this context, this alpha is insignificant. So in capturing our final equation, we don't bring that variable in our final regression equation. That is why in this context, the final equation ignored the intercept, and we only wrote the 0.330716. So the 0.330716 refers to the risk of GCB bank stocks. And since this risk of 0.3 is less than 1, we have learned in other finance courses that when the risk is less than 1, meaning that it is less risky. If it's above 1, it's what? Riskier than the market. Hello? Am I saying the right things here from your other courses you learned in finance? Hello, the beta, CAPM, that you learned earlier. And if it's equal to 1, it means that the risk on the asset is the same as the risk of the market. Is that okay? So 0.33 means that GCB stocks return is less riskier than that of the market. And therefore, if you want to interpret further, we can say that whenever there is a unit change in the market premium, okay, GCB's excess return will be 0.33. In other words, the change in the excess return of GCB will be 0.33. So one unit change in market premium will lead to 0.33 change in the GCB's excess returns. Is that okay? And a fall, since the sign was positive, a fall would also mean the GCB's excess return will fall by the same margin. So in regressions and estimations, three things are paramount. Okay. And mostly for other relationships, three key things are paramount. One is the form of the relationship, two is the degree of the relationship, and then the other one is the direction of the relationship. Okay. Some estimations might give you two, some might give you that all three. Some would even go further and break and give you other concepts. But for now, let's stick to this first three. Is that okay? The form is talking about whether or not the relationship is linear or non-linear. That is seen by the specifications you give the model. So if I go up and I refer to our model above, this model, you are seeing that the x's or the independent variables in this context, there are no higher powers of the independent variables here. Either are they appearing in an inverse form. Once the power is 1 and it's not an inverse form of the independent variable, then this relationship is a linear relationship. That's a form of the relationship. I'll give you examples further later. So the form is in describing whether the relationship is linear or non-linear. Two, the degree is telling you the strength of the relationship. How strong is this relationship? Is that okay? Just like you saw in correlations in your other courses, where the magnitude or the strength is seen in the value of the R. You were given thresholds, maybe between 0 and 0.25 is very weak, between 0.2 and so it's weak, strong, very strong. Remember those things. The same way, the degree or the strength of the relationship is also measured in this context. And like we saw in the correlations, the R measures the strength of the relationship. In the estimation above for this one, if you look at the output, you can't see any R here, but we have R squared. Remember in your quantitative methods, you learned that R squared is called the coefficient of determination. That is found by squaring the correlation coefficient. True or false?
True.
So if you want to find the R, then you can take the square root of this R squared. That will give you a corresponding R. Is that okay? And so in this context, in GCB's case, our R will be 0.477 if you took the square root of the R squared, which means that the strength of the relationship between the market premium and then the excess return of GCB is 0.4, which is relatively weak relationship. Is that okay? Hello?
Hi, sir.
Is it okay?
Yes, sir.
Then the last thing is the direction of the relationship. Is it positive, negative, or as we say, inverse or direct? Is that okay? That is seen by the sign of the coefficient. Let me go back to the graph, the table again. You see MP here, coefficient has 0.3. There's no negative sign there. So but this kind of relationship is a positive relationship. Is that okay? So they move in the same direction. So if one is increasing, the other is increasing. So in this context, whenever market premium increases, GCB's excess return will increase. And the same vein, if the market premium falls, GCB's excess return will also fall because they are moving in the same direction. So we have explained how to describe relationships in general using the form, the degree, which is also seen as the magnitude or the strength, okay, and then the direction, which is given by the signs of the estimates, okay. Any question for now? So these are examples of the specifications that can tell you whether or not the relation is linear or non-linear. Is that okay? So look at the first one on the slide. Y is equal to beta naught plus beta 1 x1 plus beta 2 x2. Because you see here, there's no higher powers of x in here. Y is not also in higher powers. This is a linear relationship between the variables. And every software has their own way of representing them in the package. Is that okay? For eViews, if you want to capture this kind of relationship in eViews, then the syntax by your extreme right is what you use. In the same, look at a similar one, that other one to be below the linear, called a double log. Here, it's when the variables that you are going to estimate, okay, you transform them to their log forms. So both the dependent variable and independent variables are transformed to the log forms. They are using the log, double log specifications. And the way it is specified has an impact on how you interpret the output. So if the variables are not transformed before they are estimated, then the interpretation I gave earlier on that 1 unit change will lead to 0.3 unit change in test return is applied. It's okay, like the first one, the linear forms, where there's no transformation of the variables. But when you use a log forms, the way you interpret the output is different. Now, instead of saying 1 unit change, say a percentage change in the different variable will lead to maybe that margin of percent change. So now it's about using the elasticity. Okay, the rate of change. Okay, not 1 unit change, but the percentage change in one will lead to the other. Okay, so how you interpret depends on the specifications of the model. You also have a situation where you leave the dependent variable in their natural state, but then you transform the independent variables. Okay, that's a lane log specifications. And you can also have log lane where the dependent variable is logged, but the independent variables are not what logged. There are a number of them. The polynomials refers to the higher powers of the x's, as you can see on the screen. The inverse is when you use the x's an inverse form, so 1 over something, okay, for the x's as the inverse forms. The dummy variables are normally used when you are dealing with some kind of categorical variables. Like for instance, if the independent variable is something like gender, male, female, or let's say color of hair, these are categorical variables. Okay, so that's one of the dummy variables. Their way of specifying is different. So maybe for gender, you can say let 0 be male, 1 be female, that kind of thing. Are you following? So in real life or economic analysis, there are times that your variables will appear in those forms. That way, we use a dummy or call what's the name? To come. I'll bring it. Let's move on. Sorry. So these are examples of how we specify models. Okay, and like I said, every software, what I'm seeing here is just for eViews presentations, but other softwares would have a way of representing them in them. Is that okay? All right. Now the key issues. We are now moving towards the section 5 and 6, and then the 3 now. The question now would be that assume anybody at all present any model and estimate. We should take the output hook, line, and sinker that it is good. And so, oh, please, the person should mute himself. We should take the result hook, line, and sinker and interpret and base our decision on other outputs? No. Just like before any product, whether food or chemical or drug, is allowed into this country, we have bodies that tests its efficacy and its implication on Ghanaians before they're allowed for us to consume. The same way, when it comes to economic models, before it is used, there are some things we must look out for before we can use them and apply them in our decisions. Is that okay? In a lighter note, like when, let me just go to where your colleague said that I should be doing it very often. When a lady decides to accept a proposal, they always have benchmarks that they would measure the proposal by before they will say yes or no to the proposal. True or false? My ladies, are we there? Hello?
We are here.
Some will say they want nowadays rich is the first item. The person must be rich. Then they look at the physicals, tall, handsome, with beard, broad chests. Am I speaking your mind, please? Hello?
Yes.
So those things you are mentioning, rich, tall, handsome, beard, broad chest, are the diagnosis, okay, of a quality or possible hazard material. In the same way, in regression 2, we have diagnosis of a good regression model. Is that okay? And the regression model is based on the assumptions that the model is clearly specified. That is one. This diagnosis are performed on 3 different components of the model. Remember, in the model that we gave you earlier, they had 3. Left-hand side, dependent variable. Then the independent variable, which we have 2. The main independent variable, and then we have the error term. Is that okay? Which the system estimates. Is that okay? So these 3 separate branches of the model are what we diagnose to assess whether or not the model is a good fitting model. The model, if it's ordinarily square, is a blue best linear unbiased estimator. Is that okay? So now we are moving to model diagnosis. Just like our ladies would have parameters to assess whether this guy will be a romantic guy or a good boyfriend or not. The same way, regressions would also have parameters or diagnosis for testing whether they are or not they are a good fit for our decision making. All right. So we use the second example in your model, okay, to as a reference example and diagnose, okay, and see whether that model and its output is reliable. Is that okay? And then we can replicate that one in subsequent models that we come across. All right. In that example, let me go back to refer to you on that page. If you have the book and you want to make reference to it. Is someone there to quicken the search for me? Okay, I think we are on section 3, unit 3, section 1 now. Unit 3, section 1. All right. If you want to refer to it as Unit 3, section 1, I think the online book I have here is page 65 and then 66. All right. So let me summarize the example there. We were that model was trying to find out whether income, education, gender, student status, and the balance on a person's credit card are able to predict a person's credit score rating. credit score rating, like we see the national ones, determine the default level of an individual when it comes to borrowing. Is that okay? So it's not common in Ghana, but elsewhere, individuals are given credit scores. So you are going to borrow any money from any bank or financial institution. Your score will determine the risk, whether or not you should approve or disapprove, or charge you a higher interest or not. Are you following? So it's a good measure of ascertaining whether somebody can be able to pay his loans on time and then completely, or the person will be in default. Is that okay? All right. So this model, and before it was built, like we've learned earlier, we need some theory to try and establish the variables that would explain the score. And we are assuming here that indeed there has been done. And what was realized that indeed, one, a person's level of income will determine the score the person would have. And it's reasonable because somebody who takes more income or salary able to pay his loan than the person who takes a lower income. Assume they are all taking the same amount of money. True or false? It's reasonable. Education in school, reasonably, if you have education, perhaps you can command higher income. Two, you also understand things better than the person who's ignorant. Is that okay? And three, gender. This is quite funny, but whether a person's gender can inform, perhaps the theory perhaps also inform this one, and so on and so forth. So these variables, these 5 variables, are seen as the predictors of what credit score of any possible applicant of a bank for a loan. That was a scenario. So we want to estimate this regression and now see, based on diagnosis, which of these ones truly explain variations in credit score, or not they collectively explain the variations as a whole. All right. So we put this model, gather our data, and this model, by way, the way it is, it's more of cross-sectional data. Is that okay? So we get the data and then we run it in our regression, in our eView software. And then we are given an output. And like I explained at that time, 3 sections are given to you: the top part, the middle part, and the bottom part, giving you different information. And mostly the bottom part would be most of the diagnosis. Is that okay? All right. The first diagnostic tool we want to consider is what we refer to as the coefficient of determination, as the goodness of fit. The goodness of fit. In other words, this one essentially is assessing the co-movement between the regressant on one hand and the regressant on the other hand. In other words, the dependent variable on one hand, independent variables on the other hand, collectively, not one by one. When they are put together, okay, is it a good fit? It tells us of the proportion of the variation in the dependent variable that is explained by the variation in the independent variables. In other words, in our example, the R squared here will tell us how much of a change that we see in the credit score is explained by education, by income, by gender, by balance. Is that okay? All of them put together, plus the error term and constant, all of them put together, how much are they explaining a change we are seeing in the credit score? Remember the example I gave you at that time about your examination grade, where we said maybe your lecturer's delivery can be a factor to determine your grade. How difficult the papers is determine your grade, and then your own study time can determine your grade. These are the known variables. But in our analysis, in our discussion at that time, I remember us accepting that if your girlfriend or your boyfriend broke up with you the night before examination, that can also potentially cause you from getting your grade. True or false? Heartbreak the night before examination. Hello.
Never. Very true.
But all these things are part of the error terms. Are you following? Those undescribed ones in the model. And so we are saying that the ones you know, how much are they explaining the change in the dependent variable? And ideally, we want a chunk portion of that variation to be explained by the known factors or variables, leaving a small portion for the other unexplained portion, the kind of a non-determination, the errors. So we want to know that the known ones should give us a higher explanatory power. In other words, as a desirable one. So when you perform any model estimations, your established variables in there, for it to be a desirable fit, photos of fit, it must give us a higher R squared. That's the intention. And I mean, if you can be able to modify those ones, you can expect to have a much change in your dependent variable. So let's say in your workforce, you said indeed when you increase salaries of employees, they are able to they are able to perform well. When you bring in clock in, you regulate their attendance, months will increase. Then what do? Increase salary, ensure that workers come to work on time by either bringing providing means of transportation for them. I can see the intervention here. When these things are done, then you're supposed to see a change in output. That's the idea. So if these two are the major variable that explain changing in worker output, then you address them, and then that should ultimately translate into increased worker output. That's the idea. So you have to make a decision based on a regression estimation model. So in this case, if we find education or gender balance, those things as key, then if you're accounting for a loan, those things are what we should be looking out for before we can approve or disapprove your loan. Is that okay?
Yes, sir.
The R squared lies between 0 and 1. In other words, it's 0 and 100%. So 0, 1%, 2%, up to 99 or 100%. It can be 0, it can be 100%, but it should not go beyond the 2. So if you estimate and get values that are outside these boundaries, then know that something is wrong somewhere. But the desirable value of the R squared is mostly, people say, about 50%. Okay. But as it approaches 1, the better. If it approaches 0, it's not really desirable. But other things really talk more, explain more than what you have put in your model. Is it okay? Hello?
Yes, sir. Yeah.
We are here.
Okay. So if you
Yeah,
check
yes, sir.
our output, what is the R squared in this output? If you can see the screen.
The R output
R squared. From this output you can see on the screen.
is 0.974195.
Yes, that's correct. So how will you explain this R? From what I've said so far.
So the R is less than 1 but greater than 0.
That's the range of where R lies. But I told
Yes,
you that
please.
R explains the proportion of variation you see
Yes.
in the dependent variable by virtue of the change in independent variables. So this says that education, gender, balance, status explains 97% of the change we see in credit score. That's interpretation.
Okay.
Okay. So the variation you see in the dependent variable by virtue of the independent variable changing. That's what the R squared means. So it explains the variation in the dependent variable as a lot of change in the independent variables. All right. Please, am I clear? Hello?
Hi.
Is it very clear? The interpretation.
Yes.
All right. So by this, I believe that whenever you see an R squared anywhere for any model, you should be able to interpret. Is my assumption right?
Yes, sir.
All right.
Yes, sir. Yes, sir. Yes, sir.
And you see that in this output to by just below the R squared, I just said R squared 2 there. Are you seeing? Are you seeing it's there?
Yes, please.
Uh-huh. The adjusted R squared, anytime you add more variables to your regression model, the R squared seems to be improving because you are now bringing in additional variables that can potentially explain the change you are seeing the different variable. Are you seeing? So the adjusted R squared punishes for extra models you put in your extra variables you put in your model. Remember, we said earlier on in model construction that what we seek in model building is parsimony, simplicity, few variables in there that can explain the phenomenon for us. We don't want complex issues, several things. It's like when you somebody's giving you um, um, an explanation or a reason why perhaps he failed to turn up for an event, and then start talking too much. You're even bored. You understand? But if he gives you a concise, to the point reason, then you are okay. But and I went this way, my friend called me, and I passed here, and it becomes very, very annoying. Are you following? Can't even decipher the weight of the reason he's even giving. Is that the reason he's giving? Because the narration appears too long. In the same context, in a similar manner, when your models are so complex with several variables, it makes interpretation and application of it in real life very difficult. So we want a parsimonious model, with least parameters. That makes things easy for us to address and to implement them. Is that okay? And so the adjusted R squared punishes you for bringing in more and more variables to your model. That's why, so before you build a model, you must read wide and now narrow down on the key things that can explain or the change you are seeing in the dependent variable. So you see in the model that in the output that you see that R squared is always less than the R squared, but they are telling the same story. Is it okay? Hello?
Hello.
Is it okay?
Yes, please.
Okay.
All right. So that's the reason for the adjusted R squared. That as you augment the model with additional variables, then you are being punished because as you put in more variables, the R squared keeps on increasing and improving. All right. That is the goodness of fit. Okay. R squared. And there is cousin just at R squared. All right. The next diagnostic tool is the information criterion. The information criterion embodies two factors: a term which is a function of the sum of squared errors, and then some penalty for loss of degrees of freedom from adding extra parameters. So you see, one punishment was given to you by the adjusted R squared. This other criterion to also has some punishment whenever you are adding or more variables to your model. The information criterion is a criterion that is applied especially when you are caught between two or more different models. Which one should I use? They have all given their output. Which model is better? We have seen one way is using the R squared. Another way is look at the information criterion. And normally, when we choose or rely on a model with a smaller information criterion, there are different kinds of information criteria I'm going to look at. Okay. So what is here? The information criterion is a function of the sum of squared errors. See, the idea of the linear regression we said is to minimize this sum of squared errors. Okay. So we want that one should be as small as possible. The information criterion should be as small as possible. So if you have two or more models and you want to choose the best one option, aside looking at the R squared, you can look at the information criterion. And we'll talk about what is called, we have three we're going to look at here: the Ikaiki information criterion, the Schwartz information criterion, and the Hanna-Quinn information criterion. Are we seeing it in the model? Let me go back to the first one first before I bring my example. The Ikaiki. Okay, there's something missing here. Hey, there's something on. One slide is missing. All right, I'll have to look for it and bring it back. Okay, so the slide that lists the information criterion is what is missing. Okay, I'm coming. Let me just quickly type it in, okay? All right. So we have the Ikaiki, the Schwartz, and the Hanna-Quinn information criteria. These are all types, okay, of the information criteria, and the same procedure or technique is applied where we look at the smallest values. I'm coming. All right. So Ikaiki, Schwartz, and Hanna-Quinn. Let me go back to our model. See, in the example we are using here, we have only one model. And so we're just forced to stick to this one. It's okay. But where we have two models, okay, then we'll look at the values of this Ikaiki, Schwartz, and Hanna-Quinn. And based on the one with the smallest value, that one model, with the smallest information criterion, will be preferable to the other. Is that okay? The Ikaiki is mostly applied because it is more robust compared to the other one, the Schwartz and then the Hanna-Quinn. Is that okay? So I have an example here. Please kindly look at the figures on the screen for me, okay? And tell me which of these. I have two models here. One with 3 independent variables, another with 4 independent variables. And observe the R squared for me, and then observe the information criterion for me, plus adjusted R squared, and comment. Let me see your views regarding the values, okay? So we can confirm our earlier submissions. So this is the first model. So if you can write for your reference, okay? So check the R squared, just that R squared, and then the Ikaiki, Schwartz, and Hanna-Quinn, the figures. I will show the next model in the next 2 minutes. So please write it down and comment for me, okay? Can you all see the screen and the figures? Hello?
Yes, sir, we are seeing it.
Okay, so put them down. The next 1 minute, I will just change your next. This is model 1. I want to take a comment and then your answer regarding which of these models is preferable based on the R squared and the information criterion, at least for the first two we have done so far. Can I change the next model? Okay, this model 2. Hey, my battery. That's small. Have you seen it? Yeah, the figures now, please. Hello. Hello.
Hello, sir.
Do you have the figures now?
Hello.
Yeah, we
So,
are the R square
okay.
fingers are there and the Akaki
So,
center
okay, sir.
square.
I want your comments comparing model 1 and model 2 based on the R squared. Okay, which of this model is preferable?
So it was only one model we saw on the screen.
Oh, I gave you 2. One is labeled model 1, is labeled model 2. So I'm going back. What is there now is model 2. Okay, so note it down. I'm going to model 1 right now. This is model 2. So write the figures down for R squared, for the Aikaki, and then for the Schwarz and Hannah Queen. So I'm at model 2 now. I'm giving you 1 minute again. Write the figures down. I'll take your comments. If you're ready, prompt me and I'll change the screen for the model 2.
Oh, okay, you can change.
I can change it
From
now. Okay.
model 1 rather.
So yes. So where we are now is model 2. I'm going to model 1. Okay. So I've changed the screen now. Come, write it down and then let's take your comments.
Model 1, let me see.
Maybe.
Okay, so we've seen it. I prefer model 2.
Hello.
Yes, sir.
So are we okay with the figures now? Do you have it now?
Yes, sir.
Okay, so based on the R squared, of these models is preferable or is a good model, fitted model?
So model 2.
The model 2.
Okay. And then based on information criteria, which one is preferable?
Information criteria. So you
Yes.
said based on information criteria.
I asked two things. One is the R squared, that is the information criterion, the Ikai key and the Schwartz.
Okay.
So model 2 has a bigger R squared compared to model 1.
Yeah.
That is true.
Yeah.
Because it is 0.41248.
Yes.
Plus 1 is 0.4124. So 2 has a
5
bigger, yes, 5 yes. What about the information criterion, the Ikai key and then the Schwartz?
Come.
So model 2.
So you see here, the 2 is giving you a bigger R. But then the information criterion is that the 2 is better because it's more what? That's a lower. No, it's model 1. Oh. 1 has I calculate 0.503. And then the Schwartz is 5.19. But model 2 has 5.07 for the Ikaiki and then 5.2 for Schwartz. So model 1 is preferable based on the information criterion.
Yeah. Yeah.
Are we all
Yeah.
clear?
Sir, please can
So
please can you go back? Okay, please can you go back what you just said? I didn't get it.
okay. We are looking at a best fitted model, a blue model, best linear unbiased estimator. You have seen that one of the ways to diagnose a model is using the R squared as a best of it. Is that okay? And I said that when the R squared approaches 1, it's a best model. If it's close to 0, it's not really desirable model because I mean other things explain better the change we see in the variable than the ones we are using in our model.
Yeah.
But for the information criterion, we are saying that it is a way of checking how we are minimizing the sum of squared errors. Is that okay? And so since the desire of the linear regression is to minimize the sum of squared errors, then we desire a lower information criterion. And we have mentioned there are 3 different types we're going to consider here. The Ikaiki information criterion, the Schwartz information criterion, and the Hanna-Quinn. Is that okay? And this is really useful when you are choosing between 2 or more models based on the information criterion. Okay. So the most preferred criterion is the Ikaiki. Okay. So you look at the figures of the Ikaiki and the Schwartz. Okay. The lowest figure is a better model than a model with higher Ikaiki information or Schwartz information criterion. Okay. So in this example I gave you, model 1 has Ikaiki information value of 5.034626. But model 2 has 5.07. So you see 5.2, 5.3 is less than 5.07. I see.
Yes. Yes.
If you compare the Schwartz to, it was 5.195 as against 5.2. So 5.1, 5.2. So you see 0.1 is less than 0.2. And so the model 1 appears to be a more preferred model compared to what? The Schwartz.
Yes.
You see how contrary the R squared for model 1 and 2 is. For model 1, we had R squared of 4.124. And then for model 2, we have 4.1248. So one's figure was less than the 2 in terms of the R squared. But the motion criterion is pointing to the model 1. I see. That's why we need more diagnosis to ensure we get a better fitting model. So, like our ladies, you see a rich guy, but he is short. Your desire is a tall guy, or you want a guy with a broad chest and a beard. And so, the same way, sometimes you can set Diagnosis will have some will be featuring here, others will be there. So you put them in aggregation and you pick the best ones. Is that okay? So we have done the two things now. We have seen the R squared and the information criterion diagnosis. Any question for now, please?
Sir,
Yes, sir.
yes. And so many, if I get it right, when it comes in terms of the R square, the higher the value, that's how you determine what to go for. That is it. So I mean, that's why we're going for the
Yes.
41 point. So, but when it comes to the ACA and the SWOT, you go for the lesser value.
Fantastic. Fantastic.
Okay, thank you very much.
We have hit the nail on the head. All right. So if you are using two models, okay, let me add to what you said. If you are using two models, instead of using the R, and I use the adjusted R squares. Is that okay? Because that one will penalize you for additional variables in the model, which will now be in line with our parsimonious principle, okay, of model construction.
So, please, did you say we should go for the adjusted?
I said if you're comparing, if you're comparing these are adjusted R squares on the two models, because especially where the one model has more variables than the other, that punishment will be more than the R squared figures itself. Is that okay? So this is when you see published articles, they will quote both the R and the R squares, so they can now see how effective the other ones are, or how fitting the other ones are, models are. Thank you. Any other question, please?
Hello, sir.
Yes, please.
Please, so regarding this model, this course,
Yes.
does it mean will only be made to identify data that are presented to us, use them to answer questions, or we'll be making calculations, define the R square and all that, or those ones are not part of our assignment or what we are supposed to know?
Okay. So from what I've seen so far, I think it's the second batch or so, right? Second batch or so. This area is more of, because I don't have a luxury of the software and you do it by yourself. You are going to interpret the output. Is that okay? Like we're doing here. So the output is given to you and you explain what it means. Is that okay? And perhaps that can inform a decision. Is that okay? There are a few areas where perhaps the calculation might be. That's why in your book, you're giving formulas without any calculations. In some few areas, you see some small calculations there. Are you following? Some proving somewhere how you derive, especially where you are using the derivatives, differentiation. Is that okay? Hello.
Okay.
So you rarely do calculation. Mostly it's just about perhaps prove how maybe this variable is obtained. Then you discuss, oh, we differentiate these factors like it's done in your model. Is that okay?
Yes,
Hello?
sir, it's okay. Yes, sir.
Mostly you are interpreting the outputs and telling us what tools are there to estimate those things. How do you go about them? Are you following? That's the general idea. All right. So you have discussed two tools now for diagnosing models. So we are now moving to the independent variable. So in this example we have used, we are looking at the income, education, gender, status of the applicant, and then the balance. These five. These are the independent variables. Let me go back to the regression model we were using earlier to confirm for you. I see the model there. CR is equal to beta naught. So IN, ED, G, S, and BL are our independent variables. So we must also diagnose the efficacy of these variables. Is that okay? How significant they are to explain. The R squared we used gave us the collective interpretation of all the variables put together and how they are explaining. we can also know how individual variables also explain the differentiations. Is that okay? That is the independent variable diagnosis. So the R talked about all of them. We'll come to another one that talks about all of them. That's the F statistics. Okay, we'll come there. So now I want to check each of these variables, which of them or is or is not significant in explaining the change we are seeing in the dependent variable. So the R gave us all of them explaining. By just that R, the independent variables tests will tell us which of these ones truly contribute to the change we are seeing in the dependent variable. Is that okay? And so we would have individual hypotheses on each of these variables. Is that okay? So for the first one, so we like you learned in your statistics how to write hypothesis, rather null and alternate. Is that okay? So the same way you put it here. You can also write it in an equation form. You can use English or words to write your null and alternate hypothesis. Is that okay? So for the first variable, which is the income level, you are saying that the beta 1 is as a null is exactly 0. In other words, it is insignificant. Income level is insignificant. In other words, it has no effect or does not really influence credit score of applicants. Then the alternative is that income level is truly a contributor to the change we see in the credit score of the applicant. But put in a more precise statistical manner, we say that the H1, which is the B hat 1, is not 0. Okay. Our income level is significant. And we know that to reject the H0, it means that you might have seen certain things. That's what we are going to now. So what would lead us to either reject H0 or will fail to reject H0? That's where we are going right now. We will look at least 3 or 4 different things that can point us to which of these hypotheses we should reject. Is that okay? Especially the null one. Is that okay? Am I clear? So at least I will not read all that I have there. When you get the material, you can see it there. So in your book as well. So we have for education, for income, for gender, and the other 2 variables. To make a decision on whether or not the null should be, let me use the unscientific term, accepted or not, then you are going to look at 4 different things. Is that okay? 1 is the standard error. 2 is the t statistic. 3 is the p values, probability values, and 4 is the upper and lower bounds that are all given to us in the regression estimations. So 4 things can lead us into accepting or rejecting the null hypothesis. Is that okay? First, the standard error of the coefficient itself, not the entire regression, but for the coefficient itself. 2 is the t statistics, okay, of the coefficient. 3 is the p-value of the coefficient, and 4 is the lower and upper bounds of the coefficient. Is that okay? All right. And these are all maths, so you can use the coefficient and the standard error to determine the t. As you can see on the screen, the t is given to us by the coefficient, which we divide by the standard error. So we'll try one briefly before we go ahead to interpret the output that we see in the screen. So these things, like I already mentioned, would point us to whether or not a variable is or is not significant in explaining the variation of the dependent variable. So for the standard error, we are saying that standard error should be less than its estimated coefficient for us to infer that that variable is truly statistically significant. In terms of the t-stats, the absolute value of the t-stats should be close to 2. So it should be either 2 or above 2 for us to conclude that the variable is statistically significant. For the p-value should be less than 0.05 level of significance. In other words, you have a confidence interval of 95%. Then, in terms of the confidence interval, the lower and upper bounds, you are saying that from the lower to the upper, 0 should not be in between. I would explain when I show you the output. Okay, so whether you're using the upper bound and lower bound, if you have negatives, there should be negative throughout. If it's positive, the lower and upper should all positive. But where we have one, the lower is negative, upper is positive, then that connotes that that variable is not significant. Please, are these points clear before I go to the output and we try and apply them there? Hello?
Yes, sir. They are very clear, sir.
All right. So based on what you have learned, let's keenly observe the outputs, okay, in our models. I'm displaying them too on the screen as well to be able to check which of them. So we are going to use the standard error, the t-stats, the p. Here, I think we didn't get the EV does not give you the lower and upper boundaries or upper levels, okay, critical levels. But we are using something like a SPSS that would give you the lower and upper limits. Is that okay? So at least what you have learned today, apply it when you see it today. Is that okay? I think your model has a page where it gave you the Excel output. So Excel also gives you the lower and upper boundaries as well. Is that okay? But using that one, the measure is that from the lower to the upper, the values in there, it should not cross 0. In other words, if you have lower being negative and the upper being positive, like a normal line, crossing 0 means that you are applying the idea of a normal line in your basic school. See, the normal line, you have negatives on the left, 0 before the positive values, the same way. So the same idea is what here. Your lower boundaries will represent the 0 negatives and then the upper positives. So when you're moving from the lower is negative and upper is positive, that is crossing 0. But where all the values are all on negative side, all on positives, then you wouldn't cross any 0. And so that variable would point to or would be a significant variable. That's the idea of using the lower and the upper boundaries. Now, in this case, let's check the values here. We start with the intercept, the C constant. You see that C has a coefficient of 1.46 and then an error of 6.004. We said that for it to be significant, the standard error should be less than the estimate. 6.0 is less than 416.2. Are we all seeing?
Yes, sir. We are saying it.
If you look at the IN, we have estimate of confidence of 2.08, standard error of 0.04. So it is less. So it appears what? For ED, we have 0.12 as against 0.4. You see, 0.4 is more than 0.12. So education is likely to be insignificant. I see.
Yeah.
If we check gender, Jane, we have 2.95. But standard error is 2.5. It is less. So it appears that it might be significant. Look at this one. Then we check the S. We have negative 98.7 and we have positive 4.3. Is what? Less than the absolute values is less than the what? The S. Then the BL we have 0.23 as again 0.003. So the standard error is less than the estimate. So it might be what? Significant. The education had not the education, rather the gender had less standard error compared to its estimates, but other things would confirm. So it is indeed good. Don't just only based on one. At least all these four, or most of these four, should confirm significance before you conclude on a variable's what significance. Is that okay? Let's move to the T stats. The measure of the T stat is what? 2 or above 2. Sometimes close to 2. So you can see 1.9 something is close to 2. Is that okay? So 2 above 2 will show the variable what's significant. All right. So let's compare again. For C, we have 24.3 above 2. So significant. For IN, we have 51.4. Then for ED is 0.30 less than 2.
Yes.
For G, we have 1.18 less than 2.
Yeah,
for S, it's 22. Total value. So 22 is more than what? 2. Then for BL, it's 2.8, also more than 2. So you see here on the T stats, C, IN, S, and BL appear significant.
Yes.
If we take, yes, please. Yes, sir.
But the S is negative 22. So
yeah, the T, we use the absolute value, not the sign.
Not
Look
the
at what
sign.
I showed you. Check in terms of the absolutes. Is that okay?
Okay.
Yeah, it is only the lower and upper where the signs are crucial. Is that okay? Using the boundaries, then the fourth criteria, that's where the signs are paramount. Is that okay? Now for this one, absolute values. Okay, all right. Now move the p-value. The constant here is 0.0000, so also less than 0.5. I see. For IN, less than 0.5. For ED, you see it is 0.7, more than 0.5. For G, it's 0.23, more than 0.05. I see. So you see here, for the G, the standard error was less than its estimates, signifying, but for the T and the P, they are saying otherwise. So out of the 3 criteria, 2 is said it is insignificant. And so you conclude indeed the E is insignificant. Are you following? So use more than one measure to conclude on a particular variable's significance or otherwise. And then the S and then the BL all obtain values of p-values of less than 0.05. So in conclusion, since we didn't have the upper and lower here, at least 2 of them must give us the same indication before we can conclude on that variable. Is that okay? 2 out of 3 at least, majority. So let's go to conclude on the variables based on these 3. All right. So the constant term is significant. Income is yes. Education is in, because education, they were all what? Not showing the same sign. And then gender is in, because gender we had 2 of them as opposed to 1. Are you following? But for S and BL, all the 3 confirmed significance. Are you following? And so we are saying that income truly explains, education does not, gender does not, students does, balance of the person's credit card also does explains the change we see in the credit score of an applicant. And so based on this, we can now derive our final regression model. See, the other one was our estimable model or our hypothesized model, our framework. Is that okay? Now, after testing, you now reduce it to your final model, where the variables that will be in there are all those who are significant in explaining the variations we see in the variable. Are we okay? And so we will rewrite the model now, leaving out those ones which were insignificant. Are you following? So that will be our final regression model. Any question before we move to interpreting the final output? Any question, please?
Oh.
Is it okay, please?
Yeah, to me it's okay.
Yes, sir, it's okay.
Okay, so now let's explain the values we have computed from the model. When we say the baseline or the intercept is 1.46.24, what does it mean? So, like I use the wage as an example to explain to you at time, the constant or the intercept is usually like a baseline. So for instance, in salary computation, government will give a minimum wage, for instance. Whether you have a first degree, master's, PhD, at least that should be the minimum you are going to take home. Is that okay? That's the baseline. Then other variables will now inform how much money you make another month. So maybe your experience, your commission on revenue that you're going to bring, those things can now go up and add. So like the C is like the minimum wage. Before other things will now go and augment. Exactly. So in this context, the C here can be the score that every applicant would have, whether you have education, whether you work, you don't work, okay, whether you are male or female, that can be the basic minimum score that is given to any applicant before other things will now come and either increase or erode that minimum or basic score. C'est clair?
Oui.
Oui.
All right. Now, for the income of 2.0800, what it means is that whenever there is 1 unit change in income, her score would all change by 2.0800. In other words, because the sign is positive, when income increases by 1, let's say 1 CD, her score would also increase by 2.08. That's the interpretation. The reverse is true. In other words, if income should also fall by 1, her score would also fall by 2.08. So the sign tells you direction. The value tells you the degree, the strength. Like I told you that time. Are you following? So I've applied the 2 ways here. Direction, degree. And to explain this one, because we're using linear forms, okay, not log linear or log, double log. And so I've said 1 unit change would result to 2.08 change. If it was logs, then we said 1% change would lead to 2.8% change in. But in this case, we're not using logs, and so it is just 1 against 2.08 unit change in the credit score. Is that okay? Similarly, for the status, because the sign is negative, that 1 unit change in student status would lead to 98.7 change. We want to be more clearer that if student status should increase by 1, the score would fall by 98.7. because of the sign. I see. Then for the balance, also a positive score. That means that if the balance should increase by 1, credit score would increase by 0.233. That is how we explain the coefficients of the regression estimates. And before you can explain, you should have checked their significance. So in research work, not every one of them is explained. Some of them just mention and you leave them. You only explain and you conclude on the ones that are significant. Is it okay?
Yes, sir.
All right. So that is now. So what you have done so far on the t-test of significance, I am going to show you the same models I gave you earlier on. Okay. I want you to check for model 1, at least let's do 1. Check to the variables are significant. Is that okay? And then if you can, read out the equation, the final equation based on that model for us. When you get the slides, you can try the model 2 in the house. So I'm showing the model 1 for you. Then you would look at the p-value, the standard error, and then the t-stats, and tell me which variables in there are significant, and then you give me the final equation. So I'm going to the screen to give you that model, and look at it, and then tell me. So model 1 is on the screen. Kindly check, you see what I've done so far, and then give me the final equation. All right. So you have 2 minutes. Okay, let me give you 3 minutes. 3 minutes to do this activity. Time starts now. I believe you can all see the screen.
Yes, sir.
All right, so look at it and then give me the final equation in the next 3 minutes. Thank you. Are we done, please? Hello. Hello. Yes. Are you ready?
I didn't get this. I'm waiting for them to explain.
So you can tell me which of them is or is not significant in this context. Kind of at least the things I've explained to you now, using the criteria.
So now here we are dealing with the R squared and the
No,
the alcohol and the shell. Oh, which one?
we are doing test of the t-test of the variables themselves, not the R square. I think that I and the R, where we look at the variables themselves, whether they are the p-value is less than 0.05, the standard error is above the estimated coefficient. So we are discussing now. Yes, please.
The estimated error of the P less than the coefficient of the
Yes, that is the one by the
the
so
1.5.
1.5. That's for the C.
Yes.
And then 0.6 is for the DPR. And then the
Yes.
0.7 is for the So which variables are significant in this context?
So the C is significant.
Okay.
The C is significant. And then the DPR is insignificant.
Okay.
Then the FDI is significant.
Okay.
And then the INF is significant.
That's correct. I believe
Thank you,
you
sir.
all got it.
Sorry.
Yes, yes,
No, so I
please.
didn't get. So I want to get. I was on it, but I was attending to something. So I just read the model and I want to get understanding. So now here we are dealing with the STD errors and the T statistics. Or which
Yes.
one are we using to do to see whether
all
it's
the-
significant or it's insignificant?
All the three: the standard error, the T statistic, and the probability value. All the three. So I gave you
So
the
yeah, I'm not
criteria.
dealing with the coefficient.
So there are ways. It's a coefficient we are dealing with. We are targeting them. But I check whether or not these coefficients are significant. Is that okay? How do you see? We see by these three things that are there: the standard error, the T stats, and then the p-value. Is that okay? There's another one too, which is not even showing here. That is the upper and lower values. They are not here. Is that okay? But at least for now, they're using these three. So the STD error, which is a standard error, okay. How do you check? You compare the standard error to its corresponding coefficient. Okay. For it to be significant, the standard error should be less than its coefficient. Is that okay? So like a colleague said, if you look at the first one, the C you are seeing on the screen, you see we have standard error of 1.515. But the coefficient is what 4.15. So 4 is more than 1.5. Or say it differently, 1.5 is less than 4.15. So C is significant. Is that okay?
So C is significant because of the
The
coefficient
standard
of
error.
it. The
Because the
standard
standard error
error
being less than
than the coefficient.
Yes.
Okay.
If you go to the DPR, see we have standard error for 0.062. Then we have 0.060. 0.062 is more than 0.60. I see.
Yeah.
So based on this, the DPR is insignificant.
It's insignificant because
yes,
the
because
error is
0 point is more than the coefficient.
It's more than the coefficient. Okay.
Yes.
So here, when the figure is insignificant, it means the error is more than the coefficient.
That is yes. That's the first criteria.
Okay.
Then to confirm this assertion, we add additional ones: the T stats and the P. Is that okay? So this is how you also interpret the T statistics. The T stat, the threshold is 2 or more. So 2.0 and above also suggests significance. Is that okay? So look at the C. Its T stat is 2.7. It is above 2. Are you seeing? Hello?
Yes, sir.
If you check DPR, look at it, the T is 0.9, below 2. So insignificant. Are you seeing? The FDI, the T is 2.1, above 2. The INF, you have minus 3.5. The T, we use the absolute value. Okay, not don't look at the signs. Absolute value for the T. Is that okay? So the T for the INF is 3.5, above 2. The INF is significant. Are you following? So you see, the T is confirming the INF by the standard error, which we saw earlier on, the FDI, so confirming the DPR as insignificant because the T is less than what 2. And furthermore, you can use the P values or the probability values. Is that okay? That's the third one. That one, we compare the P values to your level of significance, which you learned in your stats. And mostly we use the 0.05 or 5%. Remember in stats and research methods. Hello?
All right.
My lady, are you following?
Yes, sir.
So you compare the P to your level of significance. And normally one is taken as 5% or 0.05. So if the value is less than 0.05, then that variable is significant. Is that okay? So look at the first one. The C is 0.00, less than 0.05. The DPR is 0.3444, more than 0. So it is what? Insignificant. Are you following? So you see, all these three are saying or singing the same song. Are you following? Unlike the one we saw earlier on, where one of them. So the idea here that of these 3 or 4 different ways of checking whether or not a variable is significant, more of them or most of them should confirm or say the same thing before you can conclude on one of them. Is that okay? So in this example, all the 3 were giving us the same indication. So in other words, all the DPR in this case was insignificant. Is that okay? So then, given this, what will be your final regression model for this model? How will you derive your final regression model? How will you write it? So let me just say it for lack of time. I'll say it, and then you can try the model 2 in your houses. Is that okay? So GDP is equal to 4.15512 plus 0.378797 FDI minus 0.069310. That will be your final regression equation. You see, I didn't bring in DPR because DPR was insignificant. Is it okay?
Please, we didn't get you because we didn't get the
Sir, please come
Final.
again. Come again, please.
Can you write it for us to see?
Okay. Okay. I'll write it for you. Give me a second. Let me type it for you. Okay. I was shorting the figures. Okay. All right. Sure. All right. So GDP is equal to 4.155 plus 0.378, and that was let me see, 0.08 FDI, 0.0 FDI minus 0.069 IN. Can you see?
Yes, sir.
Oh, yeah. Like it.
Hello, sir.
Yes, please.
David,
So
David,
where,
those
so these
significant.
figures, where were they generated? Is
They
it
were
from
in the.
the
It is in the
model?
output.
Coefficient. Yeah, from the
Look at
coefficient.
the output. The coefficient. These are the betas.
Hello, sir.
Okay.
Yes, please. Yes.
Sir, from the model, the coefficient of the FDI is 0.036.
0.0.
36.
FDI is 0.376.
Okay. Yes, sir.
Yes,
Yes, sir. Yeah.
what was that? Was the that example we used? I'm using a different one now. This pi. So in your book, the idea earlier was to
0.378.
78. This I had a data. I had to do a live, but because of the way the thing appears, I didn't want to do a live. So I did estimations and I brought the output here. This is my own data that I used to test for you. This is how you write
Sir.
the final equation. Yes, please.
So meaning these are the insignificant value that you've seen in the equation.
No, significant.
Yes. What you
Is it?
said, these are the significant variable that we see in the equation.
In the equation.
Yes. The
Okay.
insignificant one was the DPR. And so you see, so DPR is not in here. I see.
So these are the significant values.
Yes.
Yes.
Okay. Okay. Please can you go back for them to check something?
So if you want to explain this one, okay, let me go back for you to check. Are you okay now, my boss?
Yes, sir.
All right. So when you get a material, you can try the model 2. Okay. So try and explain using the adjusted R squared through all the things I've done so far. Try and then see if you can understand and apply them there up to this point. I think it's almost time. So for today, we have looked at how to diagnose a regression model. We first considered, yes, please.
It seems, I don't know whether because I shifted attention, you didn't talk about the proof, the probability there, because we talk of the standard.
We have done all.
Okay. Because maybe I
we have done, or we have even done 2 examples of that the same thing. And I even spoke about the 4th one, but I didn't show the 4th one here. This is the lower and upper boundaries. I've done all that.
Okay. So, thank you.
Right. So we discussed. Please, any questions before I conclude?
Okay, so please let me say this still before we continue.
Okay.
I think what you just did now, I think for me, help get a little understanding of what you'll be doing for all this work. I think I'm quite okay at this point now. Now,
okay.
The second one is, I think you promised sending us the trial version of the A-view. I think we couldn't receive it from our classroom.
Yeah, I have to look at the link. Yes, please, I'll send it to you. I'll send it to you.
Okay.
But if you
Because
have
wanted
Excel,
to try-
can you use Excel for all these things? So Excel, but I'll send the link to you. I'll put a link and send it to you. So you have to download this. So I'll give you a link. You can go there and download the program and then you install. Is that okay? I'll send it to you.
Okay. Okay. Thank you, sir.
Right. So in conclusion, we have done gone through how to estimate the regression model, then look at how we interpret the model, and how we diagnose to see whether or not the model is a good fit, meeting the criterion we earlier discussed in our previous lessons. So that if it's a linear estimator, another estimator must exhibit what we call the blue features, best linear unbiased estimator. And that would mean that that model should meet the assumptions underlying the regression model. Is that okay? And so in diagnosing this kind of model, we have looked at using the goodness of fit, that's the R squared criterion. We have looked at the information criterion by way of the Ikaiki, Schwartz, and Hannah Quinn. Then we ended with a test, the t-tests of the independent variables, where we also measured significance based on 4 different criteria. That is the third error, the t-statistic, the probability value, and then the lower and the upper values. These 4 can help you confirm whether a variable is significant or not. Is that okay? Before they are included in the final regression model. There are other diagnosis that I'm going to consider in our subsequent meeting. That would help us to confirm whether or not a particular model, is a best linear unbiased estimator before we can rely on them for our decisions. Thank you. So we'll meet 7 o'clock this evening.
Hello, sir. This
Yes,
evening,
please.
7 o'clock.
Sir,
Yes,
I
please.
want to
Oh,
ask a question. Sir, to calculate
what's the
for
question?
the GDP, we use only the significant figures to calculate for the GDP.
To confirm, not calculate, to confirm.
Yes. Yeah, to confirm the GDP, do you have to use only significant values or figures to
Yes, yes. For all the
confirm that?
variables, for all of them, use the significant variables. All
Okay,
of the
so you said I'm
variables.
meeting 7 o'clock today, this evening.
Yes, for the other one.
Oh,
So, if you remember our last meeting, the first
yeah.
day we said Friday. Friday, less of you attended the meeting. Somewhere in the car, we couldn't meet properly, so we did it on a Sunday evening. Sunday
Okay.
evening too, we had about half of the class coming, and
Yeah.
at given that we would still do Sunday even instead of the Fridays because of the nature of people's work, travel, and those things.
So you saw the
So
time is set.
unless you want to bring it forward, that's okay with me. But otherwise, we
It's okay.
still want something is okay, right?
Yes.
Yes, sir.
To the other classes that ends around 4 there about. That's why we took the 7 o'clock in the evening. So let's meet 7 and then we conclude on the diagnosis. Is that okay?
All right, sir.
Well, when we
Yes, sir.
end the 7 o'clock one, then I'll send you the updated slide for reference. So all the best. See you at 7.